you can very simply write a few lines of code in scikit-learn. You can get some kind of machine learning algorithms quickly executed. But possibly understanding what is happening in the background sometimes really helps us if we are visualizing the problems in a little bit of more depth, deeper visualization. All right. So as there are no questions, I'll get started. What is the formula for adjusted R squared? Okay, it's just a simple computation. You may refer to some location, but I'm just giving. So it's R squared. I think if I'm not wrong, so or possibly no, 1 minus of 1, sorry, this is not the one. Yeah, this would be the typical formula for R squared, adjusted R squared. So basically what is that we are saying, whatever is the unexplained portion of the variance, I am adjusting that unexplained portion of the variance with the degrees of freedom for the uniform degrees of freedom. K is the number of independent variables, number of feature variables. So N is the sample size. So I'm trying to adjust for K. I'm trying to adjust for this unexplained variance for this K. And again, I'm doing a 1 minus to get back to the regression. So it's just like an adjustment for the degrees of freedom. So you can very well take this as the equation for adjusted R squared. I think you can refer to any book also, or even a Googling out will give you the formula. So just quickly, if I am wrong also, just try to correct it from there. That is what I could clearly see. Okay. So now, so here, if you clearly see, when we are going with the data science way, the regression is primarily understood as a prediction exercise. In this regression, if you had seen, I did not focus much on the significance levels of the coefficients, right? Overall R squared of the model, or probably I did not focus much on the standard error of prediction, etc. Because here, most of the times in data science, the way we approach this regression problem is from the perspective of prediction. So we would like to see what is the level of accuracy of prediction on a testing data set. And based on that, we will try to evaluate how good the model is. We do not use the typical statistical mechanisms that we use, like looking at the R squared of the model, because the primary way of approach itself, right? Okay, I'll discuss about this slightly later. So when we are doing the same linear regression using the statistical approach versus doing the same linear regression using the machine learning kind of an approach, these two are slightly or widely different. Though both of them produce the same equation internally, But my objective of the statistical way of doing the regression is to try focusing on which variables are playing a significant role, what is the so which coefficients are significant, which are insignificant. Look at the p values, look at the overall significance of the model, look at if the residuals are normally distributed or not, if there is any kind of heteroscedasticity or multicollinearity in the model. We look at so many things when we are doing it from a statistical analysis perspective. But from a machine learning based modeling perspective, the same linear regression is simply looked at as what is the accuracy of the prediction on the testing data. So because here we actually split the data into a training data and testing data, I'll come to that. But we run the model on the training data and we test it on the testing data. So that way, rather than bothering about the various attributes, the various coefficients, etc. of the model, we focus more on the predictability. If you clearly see, we would be seeing later, the stat tools as a package in Python that has a very good functions for linear regression model. Similarly, the scikit-learn, which is a machine learning package library, right? Possibly all the machine learning will do using scikit-learn only. So this also has a function for linear regression. Now these two functions, they are entirely different as far as the outputs, the output for interpretation is concerned. So this one gives you a lot of t-value, p-value, kind of all these statistical calculations. Looks at the coefficients, t-value, p-value, and all that. Whereas this one does not give anything. It just gives a coefficient. It does not give you whether the coefficients are statistically insignificant, anything. Because the focus of learning from the data is not in a machine learning world. It is purely generalization, and based on that generalization, how do I really fare on a new data? So as long as the models are typically passing on the new data, giving good results on the new data, we simply move forward. So that's what is the difference. So obviously, I will put a little bit of more structure to that difference. All right. So now, today we are going to look at some of the additional aspects. Obviously, we are going to look at some machine learning aspects today, which are again on the linear models itself. We started off with the linear regression. We tried to understand quite a various things about the linear regression. So we are going to go ahead with a little bit of more details relating to the shortcomings. We in the last class yesterday, we discussed about the typical assumptions of a linear regression and how we can incorporate those assumptions, how we can test those assumptions, etc. And we have also seen that if the assumptions typically don't go well, to what extent the model may not be a reliable model also is something that we have seen. Now, today we are going to look at a few more shortcomings of the linear regression. And if at all not linear, then probably can I go with a polynomial? So which is like a quadratic, cubic kind of regression model. So that's one thing. So we are extending the linear to the perspective of polynomial. And how do I incorporate a linear regression? Would always be more like a straight line. Anywhere you build a linear regression, it could be a straight line. But let's say if my data points are more in this format, possibly rather than a straight line, I would very well prefer a kind of a quadratic, because quadratic will give me this kind of a curve. Or possibly if I have another data points more like this, possibly I may require a cubic line. So obviously, if I go with a straight line, it might be something like this, where the errors might be quite sophisticated, quite pronounced. So in some cases, I may want to see if some kind of a polynomial function like quadratic, cubic, these kind of functions can fit to the data better, right? So that is something that we are going to look at. And we also talk about two important concepts, the regularization, which is otherwise called as lasso, which is L1, and ridge, which is L2. So these are also actually different machine learning models itself. You can execute them in scikit-learn as well. We will discuss the thing out. So we will talk about penalizing for the complexity. So this is one more thing that we are going to look at. And one of the very important concepts in a machine learning world, where we talk about the bias variance trade-off. So these are some of the concepts. So basically, first we will spend some time on outliers, how we can typically address the outlier. Obviously, there are some sophisticated techniques we have looked at in our previous class, how we identify the outliers, right? But those outliers are at the beginning itself, before I fit a model to the data. Now, after I fit, let's say, a regression model, how do I really visualize the outliers? Or if there is outlier present in the data, how would a linear regression model be affected? This is one important thing that we need to understand, right? Just without, if I don't handle the outliers properly, to what extent the regression models will get affected? That is something that we want to look at first. Then I would also bring in the concept of underfitting and overfitting, which is what is one other important concept that we have to understand in data science. So I have a small example that will cover the concepts of underfitting versus overfitting. And to avoid them, possibly I'm also bringing in the concept of regularization, where we'll talk about L1 regularization, which is called lasso, and we'll bring in L2 regularization, which is called ridge. And a trade-off between this L1 and L2 is called elastic net. So that is one more thing that we are going to look at. And finally, we would also introduce some more terminologies which we are going to use in all the machine learning algorithms moving forward. Once we start the machine learning algorithms, we will only use them because these are all the things that go into each of the algorithms. All right, so we will discuss about some of these important processes called cross-validation, leave one out cross-validation. So there are some other such kind of concepts. So just focus, this particular chapter has a good number of concepts. So in case anyone is not that comfortable with any of them, you can let me know. I can spend some more time to explain them. All right. So initially, I'm going to work with, so I'm loading. So now you see from a machine learning perspective, I'm using a lot of things from scikit-learn. So wherever I'm going to use the machine learning models, it's a direct usage from scikit-learn, because in scikit-learn, the process is very clearly given, right? Possibly once we understand some of these concepts, we would try to take up one full-fledged data set and try to work on it, right? Import warnings I think I told you yesterday, last time also, I don't remember exactly. So basically, whatever the warnings messages that we get because of compatibility issues, there could be so many things, right? So if I just want to ignore the warning messages, because when we are importing something, so possibly the compilation happened with the last version of Python, not with the current version. These are all some kind of warning messages that the system will develop. So what we say is only if it is an error you display it. If it is a warning, don't display it. That is what I am saying by doing this. How do I filter out the warnings? Right? So if I look at here, mostly we are using linear regression, which we have already used. And lasso and ridge are the penalization, but you can very well call them as the regression models in their own right. So basically, it's like two more regression models we are trying to address. And some kind of, when I talk about this different forms of cross validations, I'll explain what is this leave one out and cross validation score, etc. Okay. So on the medical expense data set, we tried to predict a simple linear regression and even a multiple linear regression. Right? So given a BMI of the person, what would be the medical expenses? We have seen that the quality of that output is not that great. So we will now look at a few more important aspects. Now, the first thing that I want to bring in is what is the importance of outliers in the data. So I just took, so if you are talking about, see, when we have plotted the actuals versus the expected. Yesterday we have done that plotting. When the BMI is 40, the expected expenses was some 18,000 or 19,000. But we had people whose BMI was 40, but they had expenses of almost 50,000. Whereas my model was predicting that the expected expenses is going to be 18,000. So that much of a huge difference. So the medical charges are way deviating from the regression plan. Now, can I treat all of them as outliers? Now, if my model is exposed to so many outliers, what does that mean? So based on that, I would be in a position to assess how well my model is going to fit. So when we are saying an outlier, we should find one or couple of observations to be way deviating from the rest. It's not that if all of them are deviating, I can't call all of them as outliers. I will have to say that the model that I have fitted itself is a defective model. Possibly I have to change the model. So we have to clearly understand that dimension. Okay. For example, if you look at this, right, I have simply, I wanted to simulate some kind of a data, right? So I'm taking a small data set here. I'm taking a small data set. So wherein I'm taking the X1 values as 10 times the random values. So whatever are the, I'm generating some 50 random values between 0 to 1. And I'm just multiplying it by 10 so that it lies between 0 to 10. Then Y1 I'm generating from X1. 2 times X1 minus 5 plus some kind of a random integer between 50. So depending on, so this value would be somewhere around 10. And so basically this is 0 to 10. So even if this goes to 10, 2 times 10 which is 22 times 10, which is typically 20 minus 550. And I am having some kind of a random number. So you could clearly see here, this is my y1. And if I'm going with plotting a scatter plot between the two, I could see that this is the way the graph has come out. Okay, so this one looks pretty much, because it's a linear equation, so it looks like there is a clear-cut relationship between x and y. So if I plot a kind of a regression line here, right, I could see that the regression line. So if you look at this regression line, I'm actually taking from the scikit-learn. I have fitted the model, and I am taking all the x values. So if you see, if x is typically your single series, then you will try to convert it either into a NumPy array, or you can very well convert it into a kind of a data frame as well. So I would try to fit the x1 and y1, and then I'm using this model. So I have this model, linear regression model. I'm fitting for the same values of x, right? I'm fitting for the same values of x. I'm taking all the values of x from 0 to 50 or 0 to 10. So I'm taking the values of x from 0 to 10, 50 different values in between. I'm using a linear space. So it will actually plot a linear space. So possibly it will split the space between 0 to 10 into 50 different intervals. So I have 50 different values of x fit, and corresponding to all those 50 values, I am predicting my y fit value. So based on those, I have definitely got the coefficient. So I know the intercept, I know the b1, which is the slope. I'm fitting my x1, y1. I'm plotting a scatter plot with x1, y1. I'm also plotting a line chart with x fit 1, y fit 1. And based on that, I could see that this is a kind of a linear regression line that has come. It looks like this line is very much aligned with the point. So it looks like overall that the linear regression is very much fitting to this data. Yeah. Seed is basically all of us, right? What we are simply saying is, generally here we are generating random numbers, right? When we are generating some random numbers, obviously all of us will get a different set of numbers, right? But if I want comparability against all of our results, we are trying to monitor, or we are trying to supervise the random values. So we are like creating what are called as a pseudo random numbers. So they are random, but they are controlled random. So what will happen is, if you and I both set the same random seed value, you and I both set the same random seed value, both of us will get the same result, same set of observation. So that way we can replicate our works also. Though we are using the word random, it is definitely not random. It is a known random. So they are still random values. You don't know how they would have got generated, but you and I will get the same set of random values. So when we are setting the same seed, now you and I have set the seed value as 9, then we will get the same result. Now, if I set 9, you set 29, both of us will get different results. Now, again, both of us set 29, again, both of us can get the same result. So you set the seed and immediately run a random number generator, we are going to get the same result. Same random number set. Is that okay? So now we have fitted the linear regression. We find that linear regression is pretty fine. Now I'm explicitly bringing in some kind of outlier into the data, wherein I have added this extra line. So everything was one and the same, except that I have added one extra line for an outlier. So when X is typically 20, the Y value was 50. Yeah, the 20th observation, I have typically made it as 50, not for the X of 20, right? The 20th observation in my data. So X would be something 10 times something. So for that one, I have made it Y value, I have made it as 50 rather than going with this equation. So I have kept that equation, but I have overwritten that equation by setting Y2 equal to 50 for the 20th observation, because we had 50 different observations altogether. So whatever was the 20th observation, I have made it explicitly as 50. Then we are plotting the scatter plot. I could see here the scatter plot is showing for some value of X, somewhere around 8 or something. The Y value is showing as 50. Now, just with one extra value, let's look at a linear regression. Earlier, the linear regression was almost passing through almost all the points very much with very few points on either side. But now with that outlier, I could see that this line was tending to shift to up. I could see most of the points are now below the line, whereas earlier most of both the points were uniformly distributed around that line, that side and this side of the line. Whereas with just one outlier in the data, my entire regression equation has changed. Right now, you could see the coefficients also. The slope has increased. Earlier, the slope was 2.03 and the intercept was -5. So basically, it's like it started off with this -5 and probably it is slightly going up with a slope of 2.03. But now we could see that the intercept became -5.54, which means it has even come down. But the slope of the line has actually increased. So instead of a line like this, now I am seeing a line like this. So just with one extra value, I am seeing that the overall slope of the line has actually increased. Now let's say I bring in one more. So possibly the fifth observation, I'm adding one more 50. So we have two different values which are looking like outliers here. Now you see I plot the code this time. Now I get a different, my intercept has actually gone up now, -2.49. So my intercept has gone up, but now I could see that the slope has come down because we had one value when X is just around 0, 1 or something, the Y value was 50. And similarly, when the X value was somewhere around 8 or something, still the Y value was 50. So with both these two extreme things lying in, so we could see that the slope has again come down to 1.89 and the intercept has become increased, -2.49. So which means if I look at all three scenarios, I could simply see that all the lines are three different lines, and we could clearly see there, we could clearly see the different lines that are there. They are the changes in the slope. The slope is changing, which means the outliers, the presence of outliers can very well change the entire structure of the model. Right? Slope is changing means the entire structure of the model is changing, and because of that, the predictability will change. Because of that, the error also will change. So that is one of the reasons we do not want our model to be more and more exposed to the outliers. It's always better to handle the outliers before building any kind of model. So just one outlier, two outliers, we have seen how much they can really impact our overall data model, accuracy of the model. So that is where, as a part of pre-processing, we always suggest that we should look at eliminating the outliers or handling the outliers. I do not use the word eliminate, handle the outliers. We'll talk about various ways of handling the outliers as such. Okay, so we can see that the three lines vary from each other significantly. So slope is changing, intercept is changing very widely. It's an indication that the overall model is different from the rest of the model. So one single outlier, the point of communicating this is, even if there is one single outlier in the whole data, it might very well have a significant impact on the coefficient. That is what is the important point that I wanted to drive. Possibly I can do the same thing with other models as well, but in a linear regression, because we can very well express the equation, know the coefficients, etc. Some of these concepts, they are well understood in the context of the regression, in the context of linear regression model itself. Now, we are also talking about the next thing is in terms of correlation between the observation. Okay, can you please explain the model fit? Please explain once. Model matplotlib in matplotlib inline is nothing but you are plotting it in this here itself, rather than plotting it to a separate file, or rather than plotting it as a separate JPG or something. We are getting the plot here itself. So most of the times we use this statement matplotlib with the inline. So inline itself means here itself, just below your code, you will get your answer. You'll get your plot. That is the plot inline. Then model.fit. So any model, as I told you earlier also, first you will initialize the model. Any model that we talk of, we will initialize the model by giving all the parameters to that model. Once you initialize it, you need to fit it. So you need to give your data, and based on that data, you have to fit it. So you know what are the parameters of the model. So you have to give what is your x1, what is your y1. So for the fit, you will see x actually is like array-like or a sparse matrix. So if it is an array-like, if it is a series, I should be converting it into an array-like. If it is a data frame, it can directly be given as a data frame. But if it is more like a series, single row or single column, I should convert it into a NP array or an ND array. So because if I have to convert it into an ND array, it's better that I define saying I require all the rows and I require a new column to be created. So which is where unidimensional is getting converted into a two-dimensional kind of a data. So a new axis is being created. So I have my x1, I have my y1. So y1 is still a series. If you look at so where is that? You look at the help file. X is array and y is array of shape n minus 1. samples or n samples, n target. So it is more like a target value. So it's like, so basically it is talking about a unidimensional kind of stuff. So that is the reason you can take y1 as it is, even if it is a series. But in case of x1, if it is a univariate, you better convert it into a kind of an NP array. So let me just see if the question. Could you tell again how to load a data? What is that? How to load a data? I did not get your. Ankit, I did not get your question. Possibly you should rephrase it a little bit more better. Okay, I'll take your question later in case after you rephrase it slightly better. So now I am also looking at the correlation between the data points as well, right? So most of the times what happens is if you are doing a univariate or if you are doing a simple linear regression, you are only bothered about one feature variable and one target variable. So there is no point of looking at the correlation between the two feature variables, right? But in our if you are doing a multivariate linear regression or a multiple linear regression, it is very much possible that the correlation between the feature variables can very well exist. Though we don't want the correlation between the feature variables, we want correlation between a feature variable and the target variable to be high. But we do not want much of a correlation between two feature variables, right? So it's always an important thing to take care of that kind of otherwise it will bring in the multicollinearity dimension as well. Now let's look at something. I wanted to introduce you to the concept of underfitting and overfitting, which is very, very important to bring in the concept of regularization as well. So let's say I'm generating one simple sine curve. I'm generating a simple sine curve of data. For that, what is that I'm saying? Just the same x which we have used earlier, right? So I'm generating some random numbers between 0 and 1. And based on that, I'm multiplying it by 10. I get a kind of, and that is my x. X is from 0 to 10. For y, I have taken sine of x plus some kind of randomization is what I have done. So I have taken 0.1 times the random value. Now, overall, it looks like my y value is going to lie something like this. So I'm getting some kind of sine curve kind of a thing. So I'm plotting the scatter plot and labeling it as x and y. And typically the title for this plot is nonlinear function. Now, if my data is more like this, and let's say I'm asked to fit a linear regression model to this. Obviously, if I fit a linear regression model, so for the same thing, I'm taking what is my x fit and y fit. So I want values between 0 to 10 for x. So 0 to 10, I'm generating some 1,000 points. And using all these 1,000 points, I'm predicting by using my linear regression model that I have used earlier. I have fitted already a linear regression model earlier and we called it as model. So I'm fitting it for all these 1,000 values. Based on that, I'm plotting the x and y, and along with that, I'm plotting a scatter plot for x and y, and I'm also plotting a line plot with x fit 1 and y fit 1. So here I could see that the intercept is minus 2.49 and the model coefficient, which is the slope, is 1.889. Now you see the graph has come more like this. So as x is increasing, I could see that the y is increasing more like this. Now I clearly do not see any relationship between the data that I have and the function that got fitted, the model that got fitted. I don't see any relation because the data is actually following a lot of curves and turns, whereas because I fitted a linear regression model, it is a pure straight line. In the real world, the data is a curve, but in the model, it has been fitted as a straight line. So obviously, I can say that the linear model does an extremely poor job of fitting to the target variable. My y's are more in a kind of sine curve kind of a fashion, but my y hat, which has been a kind of a predicted variable, is more like linearly increasing. These two are nowhere closer in terms of the fitting efficiency. So what is happening is my model is actually a kind of a model which contains so many curves and so much of complexity in it. But I ended up fitting a simple model to it. So where my data is complex, where my data is following a complex pattern, but I have fitted a simple model to that data, this kind of a scenario is called underfitting. So underfitting, possibly the best way to understand this is the actual relationship between x and y seems to be a complex relationship. Right? When I say complex relationship, possibly there could be a non-linear relationship. Possibly there could be a quadratic relationship, cubic relationship, some kind of a non-linear kind of a relationship. Whereas we ended up fitting a very simple model, which means, actually speaking, the model should be characterized, or the data should be characterized by more parameters but ended up being parameterized by only a few. So if the parameters are very few, it means that I may end up with a smaller model, simpler model. So when I'm fitting a very simple model, again, simple is not about simple to fit, right? I'm talking about underfitting. So I did not capture all the curves that are there in the data. I simply put a kind of a line to capture everything in that. Now, this kind of oversimplification is typically referred to as underfitting of the data. This kind of oversimplification is typically referred to as the underfitting of the data. So whenever we are using the word underfitting, we say the model fails to capture the overall trend of the data. My data is following this kind of a trend, whereas my model is giving me a different trend altogether. So it's not able to capture. My data is following a kind of a sine or a curvy kind of a trend, but my model is not able to capture that trend. Rather, it has given a simple straight line. And that is the reason we say when the model is underfitting, it will have a higher amount of bias, right? So what is that bias? If we have seen the same example, this is how I'm looking at the data, right? And let's say we have fitted kind of a linear model to it. So what we could see is, for this particular point, the model has fitted this value, whereas the actual value is this much. So it is not able to capture this much of variation. Similarly, probably here, the model, the actual data is here. The model has fitted here. Again, this much is kind of uncaptured. So these are the things. So what is that we are calling as a bias? It's a difference between the prediction and the truths using the model trained by a specific algorithm. So if I'm going with a linear regression model, and this is my actual data, as you can see, this is the amount of bias. So which means basically when I'm using a simpler model to capture a very complex data characteristics, that is when we say that the model is underfitted. So in case of underfitted models, the bias is going to be very high. This, I think, before we get into bias variance trade-off, this is what we need to understand. So when a model is an underfitted model, the bias will become much higher. Similarly, there is one more quality called variance. The variance will become much lower. Now, what do I mean by that? Possibly, we will, if you remember the yesterday's question, the BMI, and based on that, we talked about the charges. Now, the data was all around like this. Whereas our model was able to capture something like this. So, what is that we are saying here? The BMI, if I'm using BMI to forecast the charges, possibly the entire model was capturing only between 10,000 to 20,000. The forecast, the prediction, this model is only this much. So because of this, so even if I look at lowest values of BMI, the prediction is this. If I look at the highest value of BMI, the prediction is this one. But I see in the real world, the BMI value, the charges are pretty high. at different levels of BMI as well. And they are very low as well. So which means the volatility, the fluctuation of the charges for across the BMI levels is very high. Whereas when I go towards the predicted model, because it's a very linear model, I don't see too much of variation in the values. So what could very well happen because of that is the variation in the output that I'm going to get, which is what is the variance will be lower. So an indication here, so logically speaking, if you know the R squared that we generally define, we talk about it as total variation in the data. And here we talk about explained variation from the model. So most of the times when you are going with a simpler model to take care of a complex scenario, your explained variation will be very, very small compared to the total variation in the data. Now that is what is one of the characteristics of an underfitted kind of a data. So your bias will be very high, right? Bias, so which means your model is, so it's as good as like you have fitted a model on the data and you try to test that model on the same data. Still, the model is not able to do a good job of prediction. So that is what is the scenario of underfitment of the data to a particular model. Okay. What is the difference between the error and the bias? So if you look at, no, here we are using the word, so when we say error, we will use a squared error and things like that, right? So when we are using the word bias, we are only looking from the prediction. So by that algorithm, whatever is the prediction that the algorithm has predicted, so the error that we are actually getting, right? So that is because, so see, it's actually an error. When we are using the word bias, bias is actually an error. But that error is because of a wrong fitment of a model to the data. So that is what we call as an error that is more specific because of a bias. So we were biased towards a linear model when the data has actually conveyed a non-linear structure in it. So that is what we call as the bias. Bias is also a form of error, right? But what we are saying is, see, in general, the error could be, the model is a good model, but still there is some error. It's not because of a model problem. So possibly, if I had a data like this, and I have fitted a linear model, so it looks like a linear model is a decent fit to this data, right? So in that case, whatever I am calling as the predicted value and the actual value, I'm not calling this as a bias. I'm still calling this as an error. But where the model itself could be a different model, but I still fitted a very simplified model to it, then that error that I'm getting is what I'm typically calling as bias. Right? Because I am biased towards a simplified model where a complicate is possible. Now, variance is lower. So if you really see here, you will typically see, or probably I'll give you a theoretical scenario, when a linear regression model is a bad fit to the data. When a linear regression model is a bad fit to the data. So what will happen is, your data could be scattered like this, but the best fitting regression model would be more like this. So when your data is actually scattered between 0 to 80,000, right? Your model will predict values only between 10,000 to 20,000. So for any kind of a BMI, your model will say that the charges will be 11,000, 15,000, 16,000, 12,000. So it will only give you the predictions in a very small interval. Whereas we know that we had people with almost 80,000, 70,000 as the medical expenses. Now my model, which is a simplified model, is not able to give that much of huge difference, right? That it is not giving me that kind of predictions, that kind of range predictions. So which means it is having a high bias, because the bias is coming between the data error between the actual and the predicted, right? The error wise you could see this much of bias is there, but definitely the variance in the prediction is very low. So all the values will be around the 10,000 to 20,000 only. On the other hand, if the variance was normal, then probably I would have got the predictions between 0 to 80,000. But now I am getting the predictions only between 10 to 20,000 only. So which means the variance of prediction is much smaller. So one of the major characteristics that we notice in an underfitted model is you will find that the bias is very high. So basically it means that you look at the kind of error on your training data, you will find that that error is going to be much higher. So that is what we say, that the bias is high. And so which means possibly you should go for a slightly complex model rather than you trying to fit a simpler model. So we are more and more biased towards a simple model, whereas it's as good as saying, right? Possibly this is one more example that I can say. So your data is more looking like this, right? Even for linear regression, I'll tell you, your data is looking more like this, possibly with an increasing trend. Someone else might suggest, take the average of all these values and take the average as the prediction. Don't do any model or anything. Take the average of Y. Average of Y. Sometimes we do it in some. So if I give you some data and I ask you to do a prediction, sometimes basically what people do, they take the average and say average value is an estimated value. Rather than fitting any model or something, they simply say the average is the best fit. So average will always come like this, the graph for average, because it's a constant. So now, in this case also we are saying, probably I could have fitted a linear model like this, but I ended up with a constant like this. So linear model is like of dimension 1, of the degree 1, whereas this constant is of degree 0. So degree 0 is like a simple model, whereas I could have gone with a complex model of degree 1. So even this is a case of underfitting itself. So sometimes if I do a very simple calculations and simple models, when complex relationships are found between the data points, that kind of an analysis is called underfitting. I hope you are all clear with this, right? So where even though I am able to see a kind of a non-linear pattern in the data, but I end up fitting a linear model to the data, that's a clear case of underfitting. So what does that mean? The moment I do a kind of a correlation plot, right, that is where we want to do correlation. When I do a scatter plot or a correlation plot, if I am observing a kind of a non-linear pattern in the data, then I should not go ahead and fit a linear model to that data. That's the most important thing that we should take away from here, right? So, but let's say I want to go ahead with a non-linear model because my data is having a non-linear trend. So I want to go ahead with a non-linear model itself. Non-linear could be quadratic, cubic, I can try anything. Now, so all those polynomial, quadratic, cubic, fourth power, fifth power, all those things, they are all different kinds of polynomial functions. So we can very well work with scikit-learn even for this polynomial as well. So basically I can take the data up to the square, cube, fourth power, fifth power, etc. So that is where we are saying when I am taking a polynomial feature. So if I am taking x, y with respect to x, that is what we have been doing till now. So now in a polynomial feature, this is also a linear, but along with x, I will also take x squared, I'll also take x cube, I'll also take x to the power 4. So possibly this will become b1 times x, b2 times x squared, b3 times x cube, b4 times x power 4. So that way this model could even handle the higher powers of the specific variable that we had, rather than just taking only the linear part of the variable. It can very well handle these additional polynomial parts as well. So if we are saying we are talking about the first, second, and third degree, so for 2, it becomes 2, 4, 8, because the first degree is 2, the second degree is 2 squared, 4, the third degree is 2 cube, 8. Similarly, for 3, 3, 9, 27. For 4, it is 4, 16, 24. If you look at here, we have taken an array of 2, 3, 4. And now I am putting a polynomial features of degree 3. So I'm creating a polynomial features of degree 3, and I'm not including the bias, which means the constant term. The difference is what is the bias. So the difference can very well be fitted up to the intercept. So I'm not including that bias term. Now I'm fitting the polynomial. So polynomial features are being fitted to the data. So you are typically seeing 2, 3, 4. Now, because we talked about 3 degrees. So for 2, it becomes 248. For 3, it becomes 3, 9, 27. 4, 16, 64. So that is how by bringing in the polynomial features, we can work it out. Now let us do few things. I want to do it step by step, right? So what we will do is, we will create a polynomial features of degree 7. But we'll start in a sequential fashion. Okay. So initially I will create 2 things here. right? Here when we are creating, so here I have to introduce you to the concept of pipeline. So in a pipeline, what happens is a series of steps are executed one after the other. So it's as good as, so when I'm creating a kind of a pipeline in better projects, I will explain it later. Here I'm just introducing. So here I'm doing two steps in one single shot. Initially, I'm creating polynomial features of degree 2, which means x and x squared. So polynomial features of degree 2 is nothing but every variable. I have an x. I will use x as well as I will use x squared. So it's like two variables are coming in. So I have created those two variables, and I would also apply linear regression on the top. So there are two steps that I am performing. And when I have two or more steps that are performed in a sequential manner, I can very well create a kind of a pipeline. So when we are building some machine learning models, I will showcase to you how a pipeline can be helpful in terms of automating an end-to-end project. Right? Possibly if I have to test 5 or 6 different kinds of machine learning models, one after the other. So rather than be writing different lines of code, we say we will write one pipeline, and within the pipeline, I will put all my steps. So it's as good as it's a sequential kind of a executor. So think of it only from that perspective to start with. Okay. So now I'm calling that two steps together as polymodel. So when I'm using this polymodel, it's like it will take the features and it will execute a linear regression, and then it will give me the result. So you could see here, it will take poly features of order 2. So polynomial features, if you recollect, so we can define polynomial features, and I can typically mention what is the order. So when I am setting the order as 2, then it means that it will take both x and x squared. For anything, I say poly features, it will take both x and x squared, or to whatever order I am giving. So initially, what is that? The same x value, the one that we have taken earlier, the same sign function that we have used earlier. My fitted value is also fine. 0 to 10, I'm conducting some 5,000 values. Now I'm fitting a polynomial model. Polymodel.fit. So polymodel contains two steps. First step is it will create a polynomial features, right? So on what? The same, x and y. So whatever I am giving as x, it will create a kind of polynomial features, and then it will execute a linear regression also on the top of it. So I'll have to give the polynomial features for what I am trying to create. So this is what I'm giving as a polynomial features. And I would also typically want my y value. So I'm giving my x and y, so that for the x, it will create a polynomial features of order 2, which means it will take x and x squared, and then it will fit for the x value. So it will also predict, because here it has created the model. It will predict the values for x fit. So it will get the y fit value based on the x fit. So if I plot this, so had I taken a quadratic model, this is not a quadratic model. Yeah, this is a quadratic model, right? So if I am taking order 2, this is how it is giving me the best possible fitment. Now, possibly if I look at 3, This is what is coming out as the best possible fitment. Like that, you keep increasing. Now we are coming slightly better. Fourth order, x squared, x cube, x power 4. So fifth is looking even more better. This is the sixth. So sixth and seventh. So possibly if you go like this, of course, we are not evaluating some of the metrics, but you could see that to a large extent, we are able to fit the data points, fit the model to the data points more and more appropriately, right? But let's say you take this to 20 or something. It looks like there are so many points which are exactly fitting, but at the same time, some values are typically missing out also. And it might very well be possible you see here for x equal to 10, it is looking quite weird. And possibly you could see there are so many curves that have come out. Because in any polynomial, with every degree of polynomial increasing, you get one curve. So now, if I'm talking about a 20th degree polynomial, it means that in my graph, there will be 20 curves, though minor or major. So there will be 20 curves if I'm going with a 20th order kind of a polynomial. So what would happen in those kind of, now here also, if I've gone with a 7th degree polynomial, right, I'm seeing that there are some curves, possibly here we see some curve, here you see some curve, then one curve here, one curve. So overall, we could see that there are 7 different curves, and possibly your model, possibly with a 4 or 5 also, it is looking more or less similar. So it might be very well possible that if I increase the complexity beyond a certain point, so at least we are sure that the second degree, which is quadratic, the third degree, which is cubic, the fourth degree, they are not that heavily fitting to the data. But suddenly when I looked at the fifth degree or the sixth degree kind of polynomial, it was more or less appropriately fitting to the data. So the moment I'm seeing such a kind of appropriate fitment to the data, I should stop it. Rather than that, if I still progress further, what could happen is the model may not be a generalized model, but it would become more and more specific to each point, right? So because of that, what can happen is that kind of scenario sometimes is called overfitting. So before I go to that overfitting, few things that we'll understand. In some kind of problems, polynomial regression can very well work. We have talked about the linear regression earlier, but now I am introducing to a quadratic regression or a cubic regression or a fifth, sixth, seventh order regression. So that is what we are calling as a polynomial regression or a polynomial basis function. So this kind of a mechanism is typically called as the polynomial regression. So if we fit this, let me look at the coefficients of the model. Just for your understanding. Okay, in pipeline, I have to put the coefficients. Or without a pipeline also, we can even write it without a pipeline as well. Well, I wanted to print the polymer coefficients of the model. Otherwise, if I want to print the coefficients, I'll write it separately. From sklearn.preprocessing, I'm importing polynomial features. And we already have x values. So I'm defining the polynomial features as 2. No, here we have to define it as 7. Then I'll have to fit this to my x data. So I'm fitting this polynomial to my x. The x is this values, right? So I'm trying to fit this polynomial features towards this x. So my x is nothing but small x. So here I have to give my x and y scenario. So we are giving something like this. So you could clearly see here, we have fitted a polynomial of the 7th degree. Okay, so you could see that there are different coefficients that are coming out. So these are like, if you are seeing here, these are the 8 coefficients that are coming out in each of the iteration. For each of the x values, there are 8 different values that are coming out. So you could clearly see this is an intercept, this is for x, this is for x squared, x cubed, and so on. We have all the values that have typically created based on the, we had 7 variables, right? If I'm saying polynomial feature of 7, and I have taken these values of x. So I have taken these values of x, and I have taken the values of y. Y is created from the sine function. Based on that, I have fitted a polynomial features model to that particular data. So now I can very well generate the x and the y values, and based on that, now these are the coefficients. So basically, if I fit a model now, right? So I can very well say print poly dot coef. Oh, it does not have the coefficient of coef. Let me just see. Okay, it does not have, it cannot give me the coefficient separately. So fit and fit transform degree, it will give me as 7. Get feature names, it does not do anything better. So it's only saying a degree of 7. Once you fit a polynomial model, okay, it does not have a feature to get the coefficient separately. Okay, so I mean, in some of the features you can extract. Now, for linear regression, you can very well get the coefficients of the model. But here, you are not able to get because you are simply using your x and y, and corresponding to these x and y, you are simply fitting and then transforming the data. So if I simply say fit, I think rather than saying fit transform, if I simply say fit, hmm, get feature names, get params. No, I don't think it is giving me the coefficient, right? But I really wanted to see the coefficient. No, it is not printing the coefficients here, but probably a fit transform is it will even retransform the values also. It will compute the y values also based on the x's. So sometimes what we are saying is after a specific number of iterations, we might very well see that there is a kind of overfitting that is happening to the value. So that's the next thing that we want to understand, right? So possibly if you go much more further, 18th degree or 20th degree kind of a polynomial, you may find that there are so many curves that are there. You see there is a curve in this. So because there are 20 curves that should be there when you go with the 20th order or 18th order, you should have 18 curves. Now, some data points will come perfectly fitting on the same line, right? While some of them definitely are going away, but some data points will be perfectly fitting onto the line. So now sometimes it might give a feeling that this particular model could be a much better model because a lot of points are appearing to be perfectly fitting on the line. Because that was more and more customized to that point. It is not a generalization. It is becoming more and more customized. So it is trying to put one curve for every point, right? Probably if you look at making a polynomial with 100th order, what happened? You see here, if I fit a polynomial with the 100th order, right? I think possibly let me copy the same piece of code somewhere. I think I'll have to relook at. Is it creating a problem for me? Do I introduce the x and y again? Was the x and y values overwritten or something? Okay, I think x and y values were overwritten or something, either x or y. Now, if I fit a 30-degree polynomial here, I see that somehow, but put a 100-degree polynomial. It looks like all the points are very much on the line. It looks like all the points are very much on the line. So do you say that this model is an excellent model? Can we say that this model is an excellent model? Possibly it has taken so many turns internally, and it so happened that it has even masked. If you look at the actual data, look at the actual data here. The whole data is lying between 0 to possibly 2.5 plus or minus 2.5. That is how, or even 0 to 1. This is what is your actual data. It's a sine function. So the value is just lying between -1 to +1. Now you see the axis here for the 100th polynomial, 100-degree polynomial. So the axis is in thousands. So which means your 0 to 1 is lying almost flat, and it looks as if your data, your model is also perfectly fitting all these points. So it looks as if 100th polynomial, 100th degree polynomial is a good model for this data. But let's understand, this has not actually created a model. This has actually mugged up the data, by-hearted the data. And because of which it has done a good job on the training data, right? Because it was able to mug up each and every point, and for each and every point it has created a kind of a curve. So that's where a 100th degree polynomial was required to model these 50 points, right? So in this case, what we say is, it has actually not created any kind of a model, but it has typically mugged up the data. Right? We can see how the model fits almost all the points exactly. Now, this is where it seems like model is learning too much from the data. That is what we could see here, right? It is almost fitting every point in the data, but it is not generalizing anything. It is creating it is utilizing one extra variable for one extra point. So it's almost making it like a 1-to-1. So for every point that is there in the data, we had only 50 points, right? X is having only 50 points. So for every point, it has utilized one curve just to pass through that point. So because of that, what is going to happen is it has almost mugged up the data. It has not generalized that. So which means if I predict this model on a new data, I'm going to fail very badly. right? On one more new data, if I create or if I predict this model on the new data, what we will typically find is the error is going to be substantially higher because it's as good as, right? Possibly the explanation that I'll generally give here is, I have given you a book and I ask you to read. You have mugged up the entire book, right? You have mugged up the entire book. I have given you a question from the book. Excellent result. You did not learn, you mugged it up. I give a question from the book, you will get almost full score. But I give you a question outside the book, there is nothing that you will write. That is what is typically overfitting. So a simple way of explaining it is, on the data which is used to build the model, your model will perform extraordinarily well. But if I am giving some new data for prediction, suddenly the error is going to increase quite drastically. And that is what we typically talk about as overfitting. So overfitting occurs when the model follows the training data set very rigorously. Whatever is the data that we are using to fit our model, that is what we call as the training data. So if the training data set, every observation is given a specific attention, not a general. So what we want our model to do is, it should be able to generalize the data well. Generalizing is not equal to mugging. Generalizing is, I develop a broad patterns in the data. Whereas if I go with the multi-layered or multi-degree polynomial, it goes as if I am giving special attention to each and every data point separately, not on a larger scale. So when you are looking at with the same data where you have fitted the model, you will find that the error is very, very less. All points are perfectly fitting to the data. All the points are fitting to the model. Whereas you give a new data set, suddenly you will find the error to shoot up like anything, right? Now that means it is not actually learning anything. It's not actually generalizing anything. Rather, it has simply mugged it up. So it is as good as that example. This is sometimes I always give it. I think I have discussed the same. You are doing a by hearting. Probably if the questions are straightforward, your score is excellent. But if I give you a slightly tricky question, not from the book, it's going to have very high. So that is the reason when I have an overfitting model, the predictions can range from anything to anything. So they can be very low, they can be very high, they can go in a very, very big range. So the moment I see that my model is an overfitted model, the moment I test it on the testing data, I get wide range of values. Because we know it's a quadratic, cubic, 100th degree polynomial. So instead of 1, I put a 2. 2 to the power of 100 is going to be something. So obviously my sine curve is lying between -1 to +1. And to model that sine curve, you put a 100th degree polynomial, you can get a result of 2 to the power of 1000. So you can see the error is 2 to the power of 1000 minus 1. So you can very well see that the variation in the data is quite substantial. So that is what we call as overfitting. So basically what we are saying is, we can come across both these types of models, right? Possibly you are using a very simplified model to capture a complex relationship. In that case, there is a possibility of underfitting. So in some cases, you are fitting a very complex model where a simple model is actually sufficient enough. then you are getting into the process of overfitting. So some of the important things that we have to talk about: simpler model in complex environment, we call it as underfitting. In underfitting, we say the bias is higher, the variance is generally lower. On the other side, you are using a complex model in simple environment. So simple is relatively simple. When a third degree polynomial is sufficient, I go for a 20th degree polynomial. So I'm not saying a linear model is sufficient. Sometimes even a third degree polynomial model is sufficient. But somewhere I end up creating a 15th degree or 20th degree polynomial. So in these cases, the bias will be lower because in the model, so when I'm actually fitting my model, the gap between the actual and the predicted values is by very, very low on the training data. So that's where the bias will be much lower. The variance, which is like on a new data, when I am really looking at this scenario, definitely the error is going to be much higher. And this error is primarily because of the variance. Now, how do I address, right? So this overfitting is a very, very complex issue, is a very, very important issue that requires some kind of, because most of the times we end up fitting some complex model. So sometimes fitting a simpler model is also there, but the more serious problem comes with when I am trying to fit some kind of complex models to the data. Right? Possibly I may want to bring in more dimensions into the data. So what we say is, whenever we are sensing some kind of overfitting in the data, let me just, yeah, I'll try to wind it up in another couple of minutes. So we'll discuss about the L1 and L2 tomorrow, but I'll just introduce you to the concept of regularization here. So here what is happening is, I try to fit a complex model in a simple environment. So that is what we said, it is overfitting. Now, a simpler way of overcoming the overfitting is typically designed like this. So whenever there is an overfitting, right, we are getting more number of coefficients because we are fitting a complex model. Possibly I can have an x squared coefficient, x cubed coefficient, x to the power 4 coefficient, and so on. Now, because of this, what can very well happen is, the coefficients of the adjacent basis functions grow large and can sometimes possibly this coefficient could be like 1500, and this one would be minus 1445, 1495. So this can keep growing, and this will have a negative sign, and this will also keep growing. So finally, sometimes what we will end up seeing is a kind of extraordinary coefficients like this, right? Probably here also I may get 20,220 x power 4 minus 20,200 x power 5. So these are positive and negative, almost equal in value, and they keep going up and up and up in the process of optimization. So because of that, what can very well happen is, if I am giving a new data now, it can have a very, very serious implication, because of which I may get an extraordinary error. So overfitting, especially when we are seeing this kind of adjacent coefficient, they grow quite higher. Sometimes when you do some kind of optimization function, you will typically experience this. So especially when you are trying to give a very complex model, it will still give you the solution by giving a positive coefficient to one variable and a corresponding negative coefficient to the adjacent variable. Squares and cubes are adjusted with huge coefficient. Now, because of that, what we are saying is these coefficients will become abnormally large. Now, that is the reason this regularization, what it is aiming is, in your objective function itself, it is putting some kind of constraints on the coefficient. Regularization is actually putting an additional criteria in your objective function itself. Like in the OLS, in the ordinary least squares, we said yi minus y cap whole squared. This is what we did when we, so I wanted to minimize this, and based on this we have tried finding the coefficients a and b. So now we go one extra step and say, along with this, minimize something relating to the coefficients also. So my coefficient should not go exceptionally larger. My adjacent coefficient should not grow exceptionally larger. So penalize the coefficients if they are growing exceptionally larger. And that is what is a regularization. So we need to limit such spikes explicitly. Most of the times when there is overfitting, you will find that some of the coefficients will grow abnormally large, especially the adjacent coefficient. So we are trying to minimize that kind of a spike by penalizing large values of the model parameters. We will see that. So that kind of a regularization is called, that kind of penalization of the coefficients is what we are calling as regularization. So you can regularize with absolute value of the coefficients, which is called as L1 or lasso regularization. You can take care of the second level L2, which is like a squared values of the coefficients, which is what is called as a ridge penalization or ridge regression, and a kind of weighted average between L1 and L2, which is otherwise called as elastic net. So we will discuss about these three forms of regression. These are also kind of regression models itself. So today we looked at the linear regression and the penalized, polynomial features related regression. In the next class, we can very well look at these three, L1, L2, and elastic net. And along with that, we will also talk about aspects relating to cross-validation, etc. All right. I think I'll stop this session here. Possibly we'll spend more time on the regularization aspects in our tomorrow's session. In case anyone is having any questions, I can spend some time to discuss. Otherwise, generally, towards 8:45 and 9, I feel a bit more sleepy because I hit the bed at 9 o'clock. So, yeah, unless I don't want to take up a new topic towards closer to 9 o'clock. So we will take up this new topic somewhere in the morning, at 7 o'clock, so that we can typically put a little bit of more attention on same. Now we can discuss some doubts in case anyone is having any. I'll share the sheet.